Welcome back, deep divers. Ready for another deep dive. Today we're tackling Ramsey theory. We've got this research paper. It's called Ramsey Theoretic Characterizations of Classically Non-Ramseyian Problems.
Sounds a bit intimidating, right?
Yeah, a little bit.
Right.
But basically, it's about finding order, like even in the middle of total chaos.
Yeah, exactly. Think of it like this. You have a whole bunch of dots, and you randomly start connecting them with lines, but you're using different colors. What Ramsey theory tells us is that after a certain point, like no matter how randomly you're coloring, you're going to find specific patterns, like guaranteed.
Okay, so like a group of dots all connected by, say, red lines.
Exactly.
So I get the dots and lines thing, but what's that got to do with like prime numbers? This paper's hinting at some pretty big connections there.
Oh, absolutely. This paper, it really kind of pushes the boundaries of Ramsey theory. You know, it shows how it connects to some of the really big unsolved problems in mathematics. And yeah, you're right, especially when it comes to prime numbers and those sequences, arithmetic sequences, that have been puzzling mathematicians forever.
Like centuries, right?
Centuries.
Yeah, so are you saying we're not just talking about those colored graphs anymore?
Not at all. This paper, it takes Ramsey theory and it uses it to kind of redefine problems that traditionally people wouldn't even think of as Ramsey problems.
Okay. Can you give us an example, just a little taste of what we're getting into here?
Sure. Think about the twin prime conjecture. You know, that one that says there are infinitely many pairs of prime numbers that differ by only two, like 3 and 5 or 11 and 13.
Yeah, I remember that one from somewhere. It's a classic, right? It's one of those that's stumped mathematicians forever, hasn't it?
Exactly. And what's really cool is that this paper shows us that we can actually rephrase that conjecture. And actually, not just that one, others like it too, as statements about, believe it or not, the existence of certain types of Ramsey numbers. It's almost like we're finding this hidden bridge between number theory and graph theory.
That's wild. Okay, so before we get too lost in the weeds here, let's take it back a step. The paper starts by revisiting classical Ramsey numbers. Can you just remind us what those are?
Sure. Think of a classical Ramsey number as a kind of threshold, you know? It tells you basically how big a network has to be before you're absolutely guaranteed to find a certain pattern in it, no matter how messy or random the connections are.
Okay, I think I see what you mean. So if we're talking about, say, a network of people, the Ramsey number would tell us how many people we need at a party to guarantee that at least, say, 3 of them all know each other.
Bingo. That's a perfect example of a classic Ramsey problem. Now, the paper, it gets a bit more formal, of course. They use the language of graph theory. They define the Ramsey number. They use this notation, RZ1 below A, and it represents the smallest number of vertices that you need on a complete graph, so that no matter how you color the edges, and you can use M different colors, you're guaranteed to find what we call a complete subgraph. It's a group of Z vertices where all the edges are the same color.
So it's all about finding those unavoidable patterns, those monochromatic subgraphs, no matter how chaotically we color those edges.
Exactly. You got it. And what makes these Ramsey numbers so fascinating, and let's be honest, sometimes frustrating, is that they can get so big, so fast. You know, even for relatively small numbers of vertices and colors, finding the exact Ramsey number is, it's really hard.
Right. It's kind of like those games where you try to guess how many jelly beans are in a jar, but on a massive scale.
That's a great analogy, and that's actually one of the challenges that this paper is trying to address. They introduce some really clever tools and techniques to make these unwieldy Ramsey numbers a bit more manageable.
Okay, I'm hooked. Tell me more. What kind of tools are we talking about here? I saw something in the paper about resolution.
Ah, yes, resolution. That's key to this paper. It's like a way to zoom in to just focus on the really important parts of a Ramsey problem. We can simplify these complex situations by really homing in on what truly matters.
So it's like decluttering the problem, getting rid of all the extra stuff and seeing the core structure more clearly.
Exactly. And what's really interesting, they bring in tools from a whole different area of mathematics, algebra.
Okay.
They introduce these things called indicator polynomials, which are essentially algebraic representations of the edge colorings of graphs.
Wait, hold on. You're saying we can write equations that tell us whether or not a graph has a specific colored pattern?
Yeah.
How is that even possible?
It's pretty ingenious, really. Let me give you a quick example. It's from the paper, actually. Look at the complete graph on 4 vertices. That's denoted as K4. Okay, so let's label the edges 0, 1, 2, 3, 4, and 5. we can represent a coloring of K4 with a polynomial. It uses the variables x, 0, by 1, by 2, by 3, by 4, and by 5. For instance, this polynomial, 1 by 1 by 3 by 5, 1, 1 by 1, 1 by 3, 1 by 5, in F2xe ht4, where F2 is the finite field with two elements. This corresponds to a coloring where the edges 1, 3, and 5, they form a monochromatic triangle.
So you're saying that by constructing these polynomials in a clever way, we can actually encode information about those color patterns.
Yeah, exactly. And the amazing thing is that, these indicator polynomials, they let us translate this graph problem into an algebra problem.
So we can use algebra to help us understand Ramsey theory.
Exactly. We can use the tools of algebra, like finding the roots of polynomials, to help us understand the structure of these Ramsey problems.
That's a game changer. It's like we're unlocking a whole new set of mathematical tools to attack these problems.
You got it. And the paper takes it even further, showing how these indicator polynomials can actually help us calculate Ramsey numbers, at least for certain types of Ramsey numbers, ones that are called Galois type.
Galois type, okay. What makes them so special?
Well, Galois type Ramsey numbers, those are the ones where the number of colors we're using happens to be a prime power.
Prime power, right.
And prime powers are super important because they're directly tied to these things called finite fields. And those finite fields are essential for that polynomial approach we were talking about.
Okay, I see. So it all comes back around. The prime powers link the number theory to the finite fields. And then those finite fields let us build these indicator polynomials that help us understand Ramsey numbers.
That's it. It's a beautiful example of how these different areas of math, they all kind of come together to help us understand a problem.
And I have a feeling we're just getting started, right? This paper, it hints that these connections go even deeper.
Oh, absolutely. We've only just scratched the surface here. In the next section, we'll get into how they use those indicator polynomials to actually reformulate classic number theory conjectures.
Okay, now I'm really excited. This is going to be good. Okay, so we've laid the groundwork, right? Classical Ramsey numbers, indicator polynomials, all that good stuff. But now, let's get to the really cool part. How does this paper use those tools to reframe the biggest unsolved mysteries in number theory? That's what I'm really excited about.
Yeah, this is where it gets really mind-blowing. The paper focuses on 4 big conjectures. We've already talked a bit about the Green-Tau theorem.
Right.
But it also dives into the twin prime conjecture, Zhang's theorem, and Polignac's conjecture. And all these conjectures are all about prime numbers, how they're distributed, specifically those gaps between them.
Okay, yeah, I remember. And the paper is saying we can think about these conjectures as statements about the existence of certain types of Ramsey numbers. That's a pretty big leap, conceptually.
It is, but it's a really elegant idea. Think about it this way. Ramsey theory, it's all about finding those guaranteed patterns in systems that seem really chaotic.
Right.
And, usually we're looking for patterns in graphs, but these authors, they show us that we can apply the same logic to how prime numbers are spread out.
Okay, so instead of coloring edges in a graph, we're coloring what?
Yeah.
The gaps between prime numbers. That sounds pretty abstract.
It is abstract, yeah, but it's really cool. Imagine you have a number line, right? And you highlight all those prime numbers. Now, instead of just looking at the primes themselves, we focus on the distances between them. We can give those distances different colors.
So a gap of 2 could be red, a gap of 4 could be blue, and so on.
Exactly.
Okay, I'm starting to see it. So we've turned this number line into a kind of distance-colored graph. But how does Ramsey theory fit in here?
Well, remember how classical Ramsey numbers, they tell us how big a graph needs to be to guarantee that we'll find a certain kind of subgraph, one with all the edges the same color.
Yeah, those monochromatic subgraphs.
Right. Well, we can do the same thing with our number line. We can ask, how long does the segment of this number line need to be to guarantee that it'll have a certain pattern of colored gaps?
So, instead of looking for a subgraph with all red edges, maybe we're looking for a sequence of gaps that goes, say, red, blue, red.
Exactly. And that's how they link those number theory conjectures to Ramsey theory. Let's take the twin prime conjecture, for example.
Okay.
It says there are infinitely many pairs of primes that differ by 2.
Right, those twin primes, 3 and 5 or 17 and 19.
Yeah. Now, on our number line, those twin primes, they'd show up as red gaps, right? Because we said a gap of 2 is red.
Right.
So the twin prime conjecture is basically saying that no matter how far out you go on the number line, you'll keep finding red gaps.
Okay, I get that connection.
Yeah.
But how do we turn that into a statement about Ramsey numbers?
Well, the paper shows that the twin prime conjecture, it's actually equivalent to the existence of a certain kind of Ramsey number. And this Ramsey number is defined using our distance-colored number line. The vertices now, they're just points on the number line, and the edges are those colored gaps between the points.
So the Ramsey number would tell us how long a segment of the number line needs to be to guarantee that we find 2 points, which represent prime numbers, that are separated by a red gap or a gap of 2.
Precisely. And if this particular Ramsey number, if it exists for every possible starting point on the number line, then that means there must be infinitely many twin primes.
Wow, that's amazing. It's like we took this abstract idea of twin primes and made it more concrete by grounding it in Ramsey numbers. But what about those other conjectures like Zhang's theorem and Polignac's conjecture? Where do they fit in?
They're similar, actually. Zhang's theorem, which that was a big deal when it was proved in 2013. It says there are infinitely many pairs of primes that are less than 70 million units apart. So on our number line, that means there are infinitely many gaps that have one of the colors we assign to distances less than 70 million.
Right, so now we're not just looking for red gaps, but a whole bunch of different colors.
Yeah. And just like with the twin prime conjecture, the paper shows that we can rephrase Zhang's theorem as a statement about a certain kind of Ramsey number. This Ramsey number tells us how long a segment of the number line has to be to guarantee that no matter where we start, we'll find 2 primes that are less than 70 million units apart.
Okay, so it's the same basic idea, but we're a bit more flexible about the pattern we're looking for.
Right. And then there's Polignac's conjecture, which is even more ambitious. It says that for any even number, there are infinitely many pairs of primes that are separated by that distance.
So Polignac's conjecture is like the ultimate version of the twin prime idea. And the paper says we can rephrase that one using Ramsey numbers too.
It does. The Ramsey theoretic version of Polignac's conjecture, it's similar conceptually to the other ones, but the details are a bit trickier. It basically involves defining a whole family of Ramsey numbers, with each one corresponding to a different even gap between primes.
So for every even number, there's a corresponding Ramsey number that tells us how long our segment of the number line needs to be to find 2 primes separated by that distance.
Exactly. And the paper proves that if this whole family of Ramsey numbers, if it exists, then Polignac's conjecture has to be true as well.
Wow. This is really mind-blowing stuff.
Yeah.
It's incredible to see how all these big unsolved problems about prime numbers can be connected to Ramsey theory.
It really shows how powerful Ramsey theory is. It's not just about patterns and graphs. It's a fundamental idea about how order, it's inevitable in any system that's big enough, no matter how complex or how random it might seem.
I'm starting to get a sense of the bigger picture here. This paper isn't just about solving these specific conjectures. It's about giving us a new way to think about them, a new way to look at these mysteries of prime numbers.
Exactly. And by expressing these problems in terms of Ramsey theory, these authors, they're giving us all these new tools, new perspectives that might help us make some real breakthroughs in the future.
Yeah, that's what's so exciting about it. It feels like we're witnessing the birth of a whole new area of math, a merging of Ramsey theory and number theory that could really change how we understand both.
Absolutely. And this is just the start. There's so much more to explore here.
All right, deep divers, we're back. It's been a wild ride through Ramsey theory, hasn't it? Exploring those connections to prime numbers and those conjectures that have been puzzling mathematicians for, forever.
Yeah, it's pretty amazing. I mean, we started with the simple idea of finding patterns in those colored graphs, and now we're talking about, the fundamental structure of numbers. It's incredible.
It really is. So in this last part of our deep dive, I want to talk about, the bigger picture. The paper, it kind of hints that this is just the beginning, that there's so much more to explore here.
Oh, absolutely. The conclusion, it emphasizes this idea that while finding exact values for those Ramsey numbers, it can be a nightmare, frankly. Understanding the relationships, the structures between them, that might be the real key.
So instead of getting bogged down in all those calculations, we should be looking for those bigger connections.
Exactly. If we can understand how those numbers are related to each other, we might get a much deeper understanding of Ramsey theory as a whole and, how it connects to other areas of math too.
Okay, I like that. It's like studying a forest, right? You don't just want to look at each individual tree. You have to see how they all fit together, how they interact.
Exactly. And these authors, they point to one connection that seems especially interesting. It has to do with something called Galois connections.
Oh, okay. Galois connections. Now you're really testing my memory. Can you remind me what those are all about?
Well, think of them as like a bridge between two different mathematical structures. They help us relate those structures in a way that keeps certain properties the same.
So we could use Galois connections to link Ramsey theory to other parts of math, like maybe number theory or even abstract algebra.
That's exactly what the paper suggests. They don't go into a lot of detail, but it's definitely presented as an area that needs more research.
So it's like we've got this Rosetta Stone, and it can help us understand these hidden connections between, like, all these different parts of math.
I like that. Yeah, Rosetta Stone for math. And who knows what we might find if we look at Ramsey theory through this Galois lens.
This is really exciting stuff. Even without all those advanced connections, this paper's already shown us that Ramsey theory is way more powerful than we might have thought.
I agree. The fact that we can even think about those classic number theory problems, like that twin prime conjecture, in terms of Ramsey numbers, it shows just how versatile this theory really is.
It's like we've got these new glasses, and suddenly we can see all these familiar math problems in a totally new way, right?
Yeah.
All these hidden connections and structures just pop out.
I like that. It's a whole new perspective.
It is. And we're really just getting started. Ramsey theory is a pretty young field. There's so much more to learn.
Absolutely.
Well, deep divers, I think we've done a pretty good job, really diving deep into this research. We've seen those connections between Ramsey theory and number theory, and we've even glimpsed some of those more advanced possibilities. It's been a great deep dive. I don't know about you, but I'm definitely ready to learn more about this.
Me too.
So if you're up for a challenge, I definitely recommend checking out Ramsey theory. You never know, you might just make the next big discovery. Keep exploring the world of math and keep asking those questions. Until next time. Welcome back, deep divers. Today, we're diving into the world of Ramsey theory.
But with a twist.
Yeah, with a twist. I always love diving into Ramsey theory.
Oh, it's so fascinating.
It is. But you sent me some research suggesting there's a whole new way to look at it, going beyond those classic Ramsey numbers.
That's right.
So
the paper we're looking at today proposes a more generalized framework for Ramsey theory.
Okay.
One that could unlock new insights into some of the biggest unsolved problems in math.
Okay, now you've really got me intrigued.
Right.
Before we get to those mind-blowing connections, though,
sure,
let's make sure we're all on the same page.
Okay.
Remind me about the basics of those classical Ramsey numbers.
Okay.
And how they relate to graph coloring.
Certainly. Imagine we have a complete graph.
Okay.
Where every point is connected to every other point. Now, let's say we color the edges of this graph.
Okay.
Using a certain number of colors.
Okay.
The classic Ramsey number, denoted as ARIC, LIP, or AL, asks this question.
Okay.
How many points do we need in our complete graph to guarantee that no matter how we color the edges, we'll always find either a complete subgraph of size K with all edges the same color, or a complete subgraph of size L with all edges the same color?
So it's like saying, even if we're completely random with our coloring, some sort of order, a monochromatic subgraph of a specific size is going to pop up if our graph is big enough.
Exactly. And the challenge lies in actually finding these Ramsey numbers.
Right, okay.
For small values of K and all, we can calculate them. For instance, R3 equals 6.
Yeah, okay.
This means that in any two coloring of the edges of a complete graph with 6 points, we're guaranteed to find a monochromatic triangle.
Okay. I remember that one.
Good.
But as K and will get larger.
Yes.
Calculating those Ramsey numbers.
It gets much harder.
It gets really difficult.
Yep, absolutely. Even determining R55 is a major unsolved problem.
Wow.
But the paper we're looking at today actually doesn't focus on these specific numbers.
Okay.
Instead, it proposes this more generalized approach.
Okay, so let's unpack this generalized framework. What's the core idea here?
The key innovation is the introduction of what they call a Ramsey base.
Okay.
Instead of just considering a single complete graph, we're working with a sequence of graphs that we'll be coloring.
Okay.
Think of it as expanding our canvas.
Okay, so instead of just coloring one big complete graph, we're coloring a whole series of graphs.
Exactly.
What's the advantage of that?
Well, it allows us to ask more nuanced questions.
Okay.
And to match this expanded base, They also introduced this concept of Ramsey symbols.
Okay.
And these symbols specify the patterns or substructures that we're looking for.
Got it.
Within those color graphs.
So the Ramsey base is what we color.
Yes.
And the Ramsey symbol is the pattern we're trying to find.
Precisely.
Okay.
And then the generalized Ramsey number tied to a specific Ramsey base and a Ramsey symbol tells us at what point in our sequence of graphs are we guaranteed to find the designated pattern no matter how we color the edges?
So it's like taking the core idea of Ramsey numbers and applying it to a much wider range of scenarios.
Exactly.
Not just complete graphs and monochromatic subgraphs.
That's a great way to put it.
Okay.
Now, to really understand how this works, we need to introduce two more important concepts.
All right, hit me with them.
These are called constituent and hereditary graphs.
All right, constituent and hereditary graphs.
Okay, so imagine you have two sets of graphs.
Okay.
We'll call them set A and set B. If every graph in set A contains a subgraph that's isomorphic to each graph in set B.
Okay.
We say that set B is constituent in set A.
So constituent graphs are like the essential ingredient found in a recipe.
A great analogy.
I like that.
Good.
Now, what about hereditary?
Hereditary is a property of a single set of graphs.
Okay.
It means that the graphs within this set are ordered in a way that reflects subgraph inclusion.
Okay.
So the smaller graphs are essentially contained within the larger ones.
So a hereditary set of graphs is like a nested doll set.
Exactly.
Okay, got it.
Good.
But how do these concepts relate to this broader definition of Ramsey numbers?
Well, this generalized framework, encompassing both classical Ramsey numbers and other variations, allows us to explore a wider spectrum of Ramsey-type problems by manipulating these Ramsey bases and Ramsey symbols.
Okay, so by carefully choosing our Ramsey base and Ramsey symbol,
we
can kind of tailor our Ramsey problem to target specific patterns.
Precisely.
Okay, that's pretty powerful.
It is.
And that's just the beginning.
It's just the start.
This paper delves into some very specific types of Ramsey numbers.
It does.
Ones that connect to areas of mathematics you might not expect.
That's right.
I'm all ears.
One type they focus on is called Galois-type Ramsey numbers.
Galois-type Ramsey numbers.
And what makes these special is the number of colors we use.
Okay.
It has to be a prime power.
Prime powers. Okay, that sounds intriguing.
2, 3, 4, 5, 7, 8, 9, and so on.
Okay, why is that restriction important?
It allows us to tap into the power of finite fields.
Finite fields.
Which is a fascinating area of abstract algebra.
I'm hooked. Tell me more.
All right, so think of it this way.
Okay.
Each coloring of a graph with a prime power number of colors
Yeah.
can be represented as a point in a vector space.
Okay.
And this vector space is defined over the finite field with the same number of elements as our colors.
So each coloring becomes a point in a multidimensional space.
Yes.
And the coordinates of this point
Yes.
represent the colors assigned to the edges.
You got it. And this geometric perspective is key to their approach.
Okay.
They introduce the concept of a subgraph coloring indicator polynomial.
Subgraph coloring indicator polynomial.
Which sounds complicated, but is actually a very elegant tool.
And what exactly do these polynomials do?
It's designed to tell us whether or not a particular graph coloring contains a certain colored subgraph.
So it's like a detector.
Yes.
It scans the colored graph and signals if the desired pattern is present.
Exactly.
Right.
And the real genius of this approach is that it transforms the problem of finding Ramsey numbers into a problem of finding the zeros of these indicator polynomials.
Okay, now that's a brilliant connection.
It is.
Instead of directly searching for these complex patterns in graphs,
yes,
we can translate the problem into the language of algebra.
Exactly. And this algebraic perspective offers new avenues for tackling Ramsey-type problems.
I'm already blown away by how this generalized framework is connecting different areas of mathematics. But I have a feeling this is just the tip of the iceberg.
This is just the beginning.
What else does this paper explore?
Well, they go on to introduce a tool called X resolutions that can help simplify complex Ramsey bases, making them easier to work with.
So give me the layman's version.
Imagine you have a Ramsey base consisting of a long, maybe even infinite sequence of graphs.
Okay.
An X resolution allows us to focus on a tail end portion of this sequence and essentially chop off the beginning part.
So it's like trimming down a massive data set to a smaller, more manageable chunk.
Yes.
But how does that help us with Ramsey numbers?
The magic is that X resolutions can help us convert complicated Ramsey numbers
Okay.
into simpler ones,
All right.
which they call exact Ramsey numbers.
Okay. Hold on, back up a second.
Sure.
What do they mean by exact Ramsey numbers?
So remember those constituent graphs we talked about earlier?
Yes.
An exact Ramsey number involves a Ramsey base where the target patterns, represented by the Ramsey symbol, are constituent graphs from the start of the sequence.
So by using X resolutions,
Yes.
we're making sure that those subgraphs we're searching for
Exactly.
are present right from the get-go,
Yes.
making the problem more straightforward.
Right.
But how does that tie into the factorization of the indicator polynomials?
Well, remember, those polynomials tell us if our target pattern is present.
Right.
X resolutions essentially allow us to break down these indicator polynomials into smaller, more manageable pieces.
Okay.
Much like factoring a complicated equation into simpler terms.
I see the connection.
Good.
Like dividing and conquering
Exactly.
by simplifying the Ramsey base and factoring the polynomial.
Yes.
We can analyze these Ramsey problems piece by piece.
That's a great way to think about it.
This is all incredibly fascinating.
Good.
But you mentioned earlier that this paper
Yeah.
links to some major unsolved problems
It does.
in mathematics. Where do those connections come in?
That's where things get really exciting.
All right.
All of these techniques that we've been discussing, developed for Galois-type Ramsey numbers, can actually be applied to a much broader class of Ramsey numbers, those of locally finite type.
Okay, so we're expanding our scope even further.
We are.
What does locally finite type mean?
It means that at each level of our Ramsey base,
Okay.
the number of colors we're using is finite, but this number can change as we move through the sequence of graphs.
Right.
The key is that the number of colors is never infinite at any single level.
So it's like having a limited palette of colors at each stage.
Exactly.
But we can change the palette as we go.
You got it.
Okay.
And the amazing part is that we can apply our Galois-type techniques, which rely on finite fields, to this locally finite case as well.
Okay.
By cleverly choosing mappings that embed the locally finite structure into a Galois-type setting.
So it's like creating a universal language that allows us to talk about all these different locally finite colorings using the tools we developed.
Exactly.
Okay, that's incredibly powerful.
It really is.
This connection between Galois type and locally finite Ramsey numbers opens up a whole new world of possibilities.
It does.
Bringing us to the doorstep of those famous unsolved problems that we mentioned earlier.
Exactly.
But before we jump into those exciting connections, let's take a moment to digest everything we've covered so far.
That's a great idea.
This generalized framework is already blowing my mind.
Good.
And I can't wait to see how it all ties together.
Okay.
I'm ready for those mind-blowing connections whenever you are.
All right, let's do it. Okay, so let's bridge the gap between this generalized Ramsey theory framework and those unsolved problems.
All right.
The key ingredient that connects them is the concept of metrical colorings.
Metrical colorings.
Yeah.
I don't think I've come across that term before.
So instead of arbitrarily assigning colors to the edges of our graph, we use distances between points to determine the color. Imagine a set of points scattered in space. The distance between any 2 points dictates the color of the edge connecting them.
So instead of abstract colors, we're using a concrete, measurable property distance to define the coloring. That's a fascinating twist.
It is.
But how does this connect to those unsolved problems? Like the twin prime conjecture.
We'll get this. The famous Green-Tau theorem, which states that there are arbitrarily long arithmetic progressions within the prime numbers, can be reframed as a statement about the existence of certain Ramsey numbers.
Wait, hold on.
Yeah.
We're saying that a profound result about prime numbers can be expressed
using this metrical coloring concept
in the language of Ramsey theory.
Exactly.
Okay, my mind is already starting to bend. How does that work?
So let's break it down. The Green-Tau theorem says that no matter how long a sequence you want, you can always find a sequence of prime numbers equally spaced apart that fits that length.
So it's like finding pearls on a string.
Yes.
A great analogy.
Each pearl representing a prime number.
Exactly. All perfectly spaced.
Okay, I can visualize that.
Good.
So where do Ramsey numbers and metrical colorings come in?
So we construct a very specific Ramsey problem. Imagine our Ramsey base is a sequence of complete graphs
Mm-hmm.
where each point represents a prime number.
Okay.
We then use a metrical coloring
Okay.
where the color of an edge between two primes
Yeah.
is determined by the difference between those primes.
So the distance between primes on the number line
Yes,
dictates the color.
exactly.
I'm following so far.
Now, the Ramsey symbol in this scenario represents a path graph, which is a simple chain of points connected by edges,
Mm-hmm.
where each edge has the same color.
And this color corresponds to the spacing we're looking for in our arithmetic progression of primes.
Got it.
The existence of the Ramsey number for this specific setup proves that no matter how long a path, and therefore how long an arithmetic progression we desire, we can always find it within the prime numbers.
Okay.
This is precisely what the Green-Tau theorem asserts.
Wow. Okay, so we've cleverly translated this statement about prime numbers
We have.
and arithmetic progressions
Yes.
into a Ramsey problem
Exactly.
involving graphs, metrical colorings,
Mm-hmm.
and the existence of a specific Ramsey number.
You got it.
That's some serious mathematical gymnastics.
It is, isn't it?
And this paper doesn't stop there.
It doesn't.
It goes on to explain how the twin prime conjecture,
Yes.
the statement about infinitely many pairs of prime numbers with a difference of 2,
That's right.
can also be formulated
Yes.
in terms of Ramsey numbers.
Precisely.
Of course. It's all starting to click now.
Good.
So how do we capture the twin prime conjecture using this framework?
It's similar to the Green-Tau theorem,
Okay.
but simpler.
All right.
Our Ramsey base is still a sequence of complete graphs
Uh-huh.
with vertices representing prime numbers.
Okay.
But this time, the Ramsey symbol represents a single edge with a specific color,
Right.
the color corresponding to a difference of 2 between primes.
So by showing that this particular Ramsey number exists
Yes.
for all possible starting points,
Exactly.
we'd be proving the twin prime conjecture.
You would.
That is incredibly cool.
It is.
This Ramseyian perspective offers a fresh,
It does.
and potentially powerful lens
It does.
for tackling this age-old mathematical mystery.
Absolutely.
You know, when I first heard about Ramsey theory,
Yeah.
it sounded so abstract and niche,
Right.
but seeing how it connects to these big unsolved problems in number theory
It's amazing.
is truly mind-blowing.
It really is a testament to the interconnectedness of mathematics. What might seem like a specialized area of study can have profound implications for seemingly unrelated fields.
Absolutely. Now, we can't talk about recent progress on prime numbers
Right.
without mentioning Yitang Zhang's groundbreaking work
Of course.
on bounded prime gaps.
Yes.
Can we connect his breakthrough
We can.
to this Ramsey theory framework as well?
Absolutely. In fact, Zhang's work fits perfectly into this framework.
Okay, good.
Remember, he proved that there exists a finite bound,
Yes.
less than 70 million,
Yeah.
such that infinitely many pairs of prime numbers
Right.
have a gap smaller than this bound.
Okay.
It was a massive step towards proving the twin prime conjecture.
Right. It showed that even if we can't prove there are infinitely many
Yes.
prime pairs with a gap of 2,
Exactly.
there are definitely infinitely many pairs
Right.
closer together than 70 million.
Yes. So how do we express Zhang's result using Ramsey theory?
We follow a similar path as before.
Okay.
Our Ramsey base is still a sequence of complete graphs with vertices representing prime numbers.
Okay.
But now our metrical coloring is a bit different.
Okay.
We use 2 colors close together
Okay.
for prime pairs with a difference less than 70 million and far apart for pairs with a difference of 70 million or more.
So we're essentially grouping prime pairs into 2 categories based on their gaps.
Exactly.
And what about the Ramsey symbol?
The Ramsey symbol in this case is simply a single edge colored close together.
Okay.
Zhang's result, interpreted through this Ramsey lens,
Okay.
means that for any starting point in our prime number sequence, there exists a Ramsey number that guarantees we'll find an edge, representing a pair of primes colored close together.
Okay.
This confirms the existence of infinitely many prime pairs with gaps smaller than Zhang's bound.
This is amazing. So we have a single framework. This generalized Ramsey theory with metrical colorings that can capture not only the Green-Tau theorem.
And the twin prime conjecture.
That's right.
But also Zhang's significant contribution to the field.
Exactly. And it extends even further.
Okay.
We can express Polignac's conjecture.
Polignac's conjecture.
Yes.
That one states that for any even number, there are infinitely many pairs of primes with that specific gap between them.
That's right.
So the twin prime conjecture is simply a special case where the gap is 2.
That's right.
How would we translate Polignac's conjecture into this Ramsey language?
The setup is very similar to what we've already discussed.
Okay.
Our Ramsey base is still a sequence of complete graphs representing prime numbers.
Right.
But now our metrical coloring assigns a unique color for each possible even gap between primes.
So we'd have a color for a gap of 2?
Right.
A different color for a gap of 4?
Yes.
Another for 6, and so on?
That's right.
And then our Ramsey symbol would be a single edge.
Yes.
With a specific color representing the even gap we're interested in?
Yes, that's exactly right. Proving Polignac's conjecture in this framework would mean showing that for each even gap and for any starting point in our prime number sequence, there exists a corresponding Ramsey number that guarantees finding an edge with that specific color.
So by establishing the existence of these Ramsey numbers for all even gaps, we'd be proving Polignac's conjecture.
Exactly.
Which, of course, would also prove the twin prime conjecture.
It would.
This Ramseyian perspective is incredibly powerful.
It is.
It seems like it could offer a whole new avenue for tackling these long-standing mathematical mysteries.
It certainly holds a lot of promise.
Okay.
It not only provides a fresh way to view these challenging problems, but also opens up new tools and techniques that might help us make progress towards solutions.
It's truly remarkable how a concept that originated in graph theory, Ramsey theory, can have such profound implications for number theory.
Amazing, isn't it?
It really highlights the unity and interconnectedness of mathematics.
It does indeed. And the exciting thing is this is still an active area of research.
It is, okay.
Mathematicians are constantly exploring new ways to apply Ramsey theory, not just to number theory, but to other areas of mathematics and even beyond.
It makes me wonder what other hidden connections and unexpected applications are waiting to be discovered.
That's the beauty of mathematics. There's always more to explore, more to learn, and more to be surprised by.
You know, as we've been talking about these big unsolved problems, like the twin prime conjecture, I keep thinking back to those indicator polynomials. They seem so powerful.
They are powerful tools.
Yeah, when we discussed them earlier. Do they actually, play a role?
They do.
And how mathematicians are approaching these prime number mysteries.
Absolutely. Those indicator polynomials are key for analyzing Ramsey numbers, even in these complex settings. Remember, they essentially give us a way to algebraically detect whether or not a specific colored subgraph exists within a larger colored graph.
And by translating the problem into algebra, we can use all sorts of powerful tools and techniques to analyze these Ramsey numbers.
For example, one promising avenue of research involves developing sophisticated bounds on these Ramsey numbers. Now, calculating exact Ramsey numbers is notoriously difficult, especially as the graphs and the number of colors get larger. But even if we can't determine the exact value, establishing upper and lower bounds can provide valuable insights.
So even if we can't pinpoint the exact number, knowing it lies within a certain range can help.
Exactly. For instance, if we're studying the Ramsey numbers associated with the twin prime conjecture, establishing tighter and tighter upper bounds on those numbers could help us inch closer to a proof.
So instead of directly attacking these notoriously difficult conjectures, researchers are focusing on bounding the associated Ramsey numbers.
Exactly.
Hoping to chip away at the problem from a different angle.
It's a testament to the ingenuity and creativity of mathematicians, constantly seeking new tools and perspectives to tackle these age-old problems.
Now, I'm curious about those indicator polynomials themselves. We talked about them conceptually, but I'd love to see a concrete example to really grasp how they work.
Let's revisit that simple example we touched on earlier. The complete graph K4. Two colors, represented as 0 and 1. And the target subgraph K3, a triangle that we want to find in a monochromatic coloring.
I remember that. So we'll have two indicator polynomials. One for each possible monochromatic coloring of K3.
Exactly.
All zeros or all ones?
Let's start with the polynomial for the all zero coloring. Remember, each edge in K4 can be colored either 0 or 1. We'll use the variables by 1, by 2, by 3, by 4, by 5, and by 6 to represent the colors assigned to the 6 edges of K4. If an edge is colored 0,
Yeah.
the corresponding variable will be 0.
Okay.
If it's colored 1, the variable will be 1.
So those variables are like placeholders for our color choices.
Exactly.
I'm with you so far.
The indicator polynomial for K4, K3, and the all 0 coloring looks like this.
Okay.
1 by 1 by 2 by 3, 1 by 1 by 4 by 5, 1 by 2 by 4 by 6, 1 by 3 by 5 by 6.
Wow, that's a mouthful. But I think I see the structure.
Okay.
Each term in parentheses corresponds to one of the 4
That's right.
possible triangles within K4.
For example,
Okay.
the term 1 by 1 by 2 by 3 corresponds to the triangle
Yeah.
formed by edges 1, 2, and 3.
Okay.
If all 3 edges are colored 0, meaning by 1, by 2, and by 3 are all 0,
Yeah.
then the entire term becomes 1, 0,
Okay.
which equals 1.
I see.
Okay.
So if a triangle is monochromatic with color 0,
Yes,
its corresponding term in the polynomial evaluates to 1.
that's right.
What happens if even one edge in that triangle is colored 1?
If even one edge is colored 1,
Okay.
its corresponding variable will be 1,
Yeah.
and the entire term in parentheses will become 0, right?
Right, because we're multiplying.
Exactly.
So if any one of the triangles is not monochromatic with color 0,
Yes,
the entire polynomial will evaluate to 0.
that's right.
So this polynomial acts like a filter,
It does.
outputting 1 only if all 4 triangles within K4 are monochromatic with color 0,
That's a great way to put it.
and outputting 0 otherwise.
It's a very elegant way to encode that condition.
Okay.
Now we can construct a similar polynomial for the all 1 coloring.
Oh, what?
1, 1 by 1, 1 by 2, 1 by 3, 1 by 1, 1 by 4, 1 by 5, 1 by 2, 1 by 4, 1 by 6, 1 by 1 by 3, 1 by 4, 1 by 6, 1.
I see how that works.
Yeah.
So each term will evaluate to 1
Yeah.
only if all the corresponding variables are 1,
Exactly.
meaning the triangle is colored all 1s.
Precisely. Now remember that R3 is 6.
Yes.
Meaning any 2 coloring of the complete graph K6 will contain a monochromatic triangle.
Mm-hmm.
If we were to construct the indicator polynomials for K6,
Yeah.
which would be much longer,
Yeah, back.
we'd find that for every possible coloring of K6,
Okay.
at least one of our 2 polynomials would evaluate to 1.
That's incredible. So it's a concrete demonstration
Yes.
of the power of these polynomials.
Right.
They provide an algebraic way to verify
Right here.
this fundamental Ramsey property.
Exactly. And this approach scales beautifully.
Oh, yeah.
As the graphs and the number of colors increase,
Yeah.
these polynomials provide a systematic and powerful way
Oh.
to analyze Ramsey numbers.
This has been such an enlightening journey.
It has been fun.
We started with those classic Ramsey numbers,
Right?
explored this incredible generalized framework,
Yes.
even saw how it connects to unsolved problems in number theory.
It's amazing.
And all along the way, these indicator polynomials have been working behind the scenes,
Yes.
helping us understand and
yeah.
analyze these complex structures.
It's a testament to the beauty and depth of mathematics.
It really is.
What might seem like a simple concept,
Right.
coloring graphs, leads to a world of interconnected ideas
Absolutely.
and profound implications.
And it makes me wonder what other hidden connections
Right.
and surprising applications are waiting to be discovered.
Who knows? Maybe one of our listeners will
Yeah.
be the one to make the next breakthrough in Ramsey theory.
That would be awesome.
That would be fantastic.
Well, a huge thanks to you for guiding us through this fascinating deep dive.
Oh, it's my pleasure.
And to our listeners, keep exploring, keep questioning, and keep diving deep into the world of knowledge.
Yes.
Until next time. Welcome to another deep dive. Today we're taking a close look at Ramsey Theoretic Characterizations of Classically Non-Ramseyian Problems by Bryce Christopherson. This paper really delves into the depths of Ramsey theory, exploring connections to problems in number theory that, honestly, I never would have imagined.
It's quite a fascinating paper, for sure. Christopherson's approach is pretty bold, you know? He's taking the concept of Ramsey numbers and stretching it way beyond traditional graph theory. Essentially, he's building a whole new framework, one that lets us express problems that seem completely unrelated, like the twin prime conjecture, in the language of Ramsey theory.
That's what really caught my attention. It's like, we know classical Ramsey numbers can be a real headache to calculate, but Christopherson seems to be suggesting maybe instead of getting bogged down in those specifics, we should focus on the relationships between these numbers, like their behavior as a whole.
You got it. It's about understanding the underlying structure, the essence of these numbers, rather than chasing after exact values in every single case. He's saying maybe that's where the real insights lie. And to get there, he expands the scope of what a Ramsey number can even be, going way beyond just graphs.
So how does he actually build this new framework? The paper starts off with a pretty dense set of definitions. Can you walk us through some of the key concepts?
Definitely. Let's start with graph colorings. They're represented by this notation, hom, GA. Imagine you have a graph, G, which is just a bunch of vertices connected by edges. A coloring is just a way to assign colors to those edges. And A, that represents the set of colors you're allowed to use.
Okay, so it's kind of like coloring a map, right?
Yeah.
Where you can't have two countries next to each other with the same color. But what's the significance of this home notation?
Looks a bit intimidating at first glance. It's just a fancy way of expressing the idea of a function, a mapping. In this case, hom, GAA, is like a container for all the possible ways you can color the graph G using colors from the set A. You can think of each coloring as a function that assigns a color to each edge.
Gotcha. So the notation makes sense now, but then the paper brings up isomorphism sets, written as GX. What exactly are those?
Okay, so picture this. You have two graphs, G and X, where X is smaller than G. The isomorphism set GX, it basically holds all the different ways you can fit the graph X into the bigger graph G without changing X's structure. Think of it like trying to fit a small puzzle piece, X, into a larger puzzle, G. There might be a bunch of ways to do it, and each way is like an element in that isomorphism set.
So it's not just about finding one copy of X within G. It's about finding all the different ways X can fit without changing its own shape, right?
Exactly. And each fitting, it's represented by a map. They use the Greek letter for that. These maps, they make sure the connections between the vertices in X stay the same as they're placed within G. The paper even gives us a solid example, K4, K3. This represents the isomorphism set of fitting a complete graph with 3 vertices, K3, which is basically a triangle, into a complete graph with 4 vertices, K4. Turns out that set has 24 elements. That's how many ways you can fit a triangle into a slightly larger complete graph.
That example definitely helps. It makes the whole concept a lot clearer. So, armed with these definitions, how does the author redefine classical Ramsey numbers?
He uses these very ideas, graph colorings and isomorphism sets, to give classical Ramsey numbers a bit of a makeover. Remember, the classical Ramsey number, RK, tells us the smallest number of vertices you need in a complete graph, so that no matter how you color the edges with 2 colors, you're guaranteed to find either a complete subgraph of size K in the first color, or a complete subgraph of size L in the second color.
Right. It's that idea of finding order in chaos. Like even if you color the edges totally randomly, if the graph is big enough, you're bound to find these specific monochromatic subgraphs.
Precisely. Christopherson takes that same idea, but expresses it with the language of graph colorings and isomorphism sets. Instead of talking about finding a specific subgraph directly, he talks about finding an element of a specific isomorphism set within a particular set of colorings.
So is this just a change in notation, or is there a deeper shift in perspective happening here?
It's more than just notation. By reframing it this way, he sets the stage for his generalized Ramsey numbers. These generalized numbers, they aren't stuck with just single graphs anymore. They can involve sequences of graphs and much more complex relationships between them.
Oh boy, that sounds like we're about to ramp up the complexity.
It does get more complex, definitely, but the core idea stays the same. We're still looking for patterns emerging within larger structures, but now those patterns can be way more intricate, and the structures themselves can be much more sophisticated. To handle this, he introduces constituent and hereditary graph sets.
Let's break this down a bit. What exactly are constituent and hereditary graph sets, and how do they fit into this generalized framework?
A constituent graph set, written as CH, is basically a collection of graphs that guarantee a certain relationship between 2 other sets of graphs, G and H. Each graph in G has to contain a copy of every graph in H. Think of it like making sure all the pieces of puzzle H can fit into each puzzle in the set G.
So it's like a condition of containment. Every graph in G must contain all the graphs from H in some way.
You got it. Now, a hereditary graph set, denoted by G, adds a bit of order to this containment. If a graph, G, belongs to this set, then any smaller graph inside G also belongs to the set. Imagine it like a family of graphs, where the children inherit the property of belonging to the set from their parents.
So the smaller graphs inherit their membership from the larger ones, like a nested hierarchy of graphs. How do these sets actually relate to the generalized Ramsey numbers, though?
These sets are the building blocks. They're what we use to define those generalized Ramsey numbers. And to capture the crucial information, he uses the terms Ramsey base and Ramsey symbol.
Okay, let's dive into those. What exactly are Ramsey base and Ramsey symbol?
A Ramsey base, written as GS, is a pair, G is a hereditary set of graphs, and S is a collection of, let's say, allowed colorings for those graphs. This base sets the playing field for us. It tells us the types of graphs we're working with and the ways we're allowed to color them.
So it's like defining the rules of the game, right? Where they can only use these specific graphs and these specific colors. What about the Ramsey symbol? How does that fit into the picture?
The Ramsey symbol, which we write as XC, is pretty similar. It's a collection of sets of graphs X and their corresponding coloring C. This symbol tells us the specific patterns we're trying to find within those colored graphs.
So the base is like the where and the how of the coloring, and the symbol is the actual patterns we're on the hunt for.
Bingo! You nailed it. And with those two pieces, the author defines the generalized Ramsey number. It's the smallest index and where a specific condition holds true. This condition involves finding, within the colorings allowed by our Ramsey base, an element of the isomorphism set that's defined by our Ramsey symbol.
Okay, it's all starting to click now, but the paper also throws in all these constraints on these generalized Ramsey numbers. Things like locally finite, maximal, and uniform. Why are these constraints so important?
Those are there to help us manage this huge universe of possible Ramsey numbers. It's like organizing them into different categories. For example, a locally finite Ramsey base means we have a finite number of colors for each graph in the sequence, though it can change from graph to graph. But a finite Ramsey base, that means we use the same finite set of colors for all the graphs in the sequence.
So locally finite is more flexible with the coloring, while finite is stricter, enforcing uniformity across the board. And what about maximal and uniform? What do those constraints tell us?
A maximal Ramsey base is like saying anything goes. We're allowing any possible coloring of the graphs in the base, giving us the widest range of options. On the other hand, a uniform Ramsey symbol means the specific patterns and colors we're looking for in the graphs stay consistent throughout the entire sequence. It's like having a fixed blueprint for the pattern we're hunting down.
So these constraints let us focus on specific types of Ramsey numbers that share certain characteristics. This categorization must be super helpful for developing specific techniques to study and analyze these numbers.
Exactly. It lets us break things down into more manageable chunks. And the paper highlights two types that are particularly interesting: exact and Galois type.
Those sound intriguing. What makes exact and Galois type Ramsey numbers stand out from the crowd?
An exact Ramsey number has this neat property. The target graphs we're searching for, the ones defined by our Ramsey symbol, they actually show up as subgraphs within the base graphs themselves. This makes them easier to analyze because we know the patterns we want are already present in the building blocks of our structure.
So it's like knowing the puzzle pieces we need are definitely somewhere in the box. That definitely simplifies things. What about Galois type? That one sounds a bit more mysterious.
Galois type refers to Ramsey numbers, where the number of colors we can use is a prime power. That's just a prime number raised to some positive integer. This type pops up all over classical Ramsey theory, and now Christopherson is bringing it into the realm of these generalized Ramsey numbers.
That connection to classical Ramsey theory is really interesting. It's like he's bridging the gap between the familiar and the new. He's showing how these generalized numbers are built upon the foundation of what we already know.
Precisely. He's saying, hey, these new, more complex Ramsey numbers aren't completely alien. They have deep roots in the classical theory. And by understanding these connections, we can use the tools and insights we've already developed to tackle these tougher problems.
This feels like a good point to take a breather and reflect on everything we've covered so far. It's clear that Christopherson is building a really robust and intricate framework for studying these generalized Ramsey numbers. He's given us the core definitions, introduced the concepts of Ramsey bases and Ramsey symbols, and laid out these constraints that help us organize and analyze these numbers in a more effective way.
Absolutely. He's laid a solid foundation for some exciting stuff. In the next part of our deep dive, we'll explore the tools and techniques he brings to the table to actually tackle these generalized Ramsey numbers, especially those indicator polynomials you mentioned earlier. They're fascinating.
Yes, those polynomials sound like incredibly powerful tools in the world of Ramsey theory. I'm really curious to see how he puts them to work to unlock the secrets hidden within these complex mathematical structures.
Welcome back. Before we jump into the thick of things, I have to point out how cleverly Christopherson sets us up to tackle these complex Ramsey numbers. He introduces this really cool technique called resolutions to simplify the problem.
Yeah, that section definitely caught my eye. It seems like resolutions give us a way to break down a Ramsey base into smaller, more manageable pieces without losing any crucial information about the Ramsey number itself.
Exactly. It's like a strategic simplification. A resolution lets us trim a Ramsey base, removing graphs that don't actually contain the target graphs we're searching for. And the best part is the paper proves a theorem showing that this simplification, it doesn't actually change the value of the Ramsey number.
So we can essentially prune the Ramsey base without affecting the final result.
Yeah.
That's pretty neat. Why does that even work? What's the intuition behind it?
It works because the graphs we're removing, they're not contributing to the patterns we're interested in. Remember, the Ramsey number is all about the smallest size needed to guarantee a stellific pattern shows up. If a graph in the base is too small to even contain that pattern, it's basically irrelevant to figuring out the Ramsey number.
That makes perfect sense. It's like getting rid of dead ends in a maze. We're not changing the destination, just making the path a bit more direct. Is there a connection here to other areas of math? The paper hints at something about resolutions in homological algebra.
That's a really interesting observation. The idea of simplifying a complex structure without changing its core properties, that pops up all over mathematics. Homological algebra, it uses resolutions to study algebraic objects by breaking them down into simpler pieces. It's pretty cool to see a similar concept at play in Ramsey theory.
It really shows you the power of abstract mathematical ideas and how they can connect these seemingly totally different fields. But let's move on to what I think is the most exciting part of the paper. Indicator polynomials. These things seem like incredibly clever tools for analyzing Ramsey numbers.
They really are. Indicator polynomials, they're like these mathematical detectors that help us find the specific patterns we're looking for in colored graphs. They're carefully designed polynomials that only vanish, meaning they equal 0, if and only if a specific colored subgraph exists within a larger colored graph.
So it's like having a mathematical searchlight that only shines on the patterns we care about.
That's a fantastic analogy. And these polynomials aren't just telling us if the pattern is there, they can actually help us figure out the exact Ramsey number associated with that pattern.
That's incredibly powerful. Can you give us a concrete example of how these indicator polynomials actually work in practice?
Sure. Let's take a simple example. The indicator polynomial for K4, the complete graph on 4 vertices, and we're looking for monochromatic triangles, K3 within it. We'll use 2 colors, let's say red and blue. The indicator polynomial for this scenario is a function of variables, and each variable represents the coloring of a specific edge in K4. If an edge is red, its variable gets the value 0. If it's blue, the variable gets the value 1.
So each coloring of K4 gets translated into a unique set of values for these variables.
Yep. And the way we design the indicator polynomial, it only equals 0 when you plug in those values. If and only if there's a monochromatic triangle in that specific coloring of K4. If there's no monochromatic triangle, the polynomial will give you some non-zero value.
It's like a mathematical filter, sifting through all the colorings and only letting through the ones that have the pattern we want. But how do we actually build these indicator polynomials in the first place? That seems like the tricky part.
Building them involves some algebraic maneuvering, but the key is to leverage the properties of the specific subgraph we're hunting for. In our triangle in K4 example, we'd construct the polynomial so that it factors in a way that mirrors the structure of a triangle. Each factor would correspond to a potential triangle within K4. The polynomial would only equal 0 if at least one of those factors goes to 0, which would tell us a monochromatic triangle is present.
So we're essentially encoding the shape of the subgraph into the algebraic structure of the polynomial.
Precisely. And the amazing thing is, this method can be extended beyond simple cases like triangles in K4. The paper shows that indicator polynomials can be used to analyze even more general cases, like locally finite type Ramsey numbers.
That's really impressive. These polynomials seem like incredibly versatile tools for studying Ramsey numbers in all sorts of scenarios.
They really are. And as we dig deeper into their properties, we start to see how they reflect the behavior of the Ramsey numbers themselves. For example, the paper shows that if we make the patterns we're searching for more complex, like using more colors or looking for larger subgraphs, the corresponding Ramsey numbers actually tend to get smaller.
Wait, really? That seems counterintuitive. You'd think searching for more complex patterns would require bigger graphs, leading to higher Ramsey numbers.
It is a bit surprising, but it highlights an important insight. By making the patterns more restrictive, we're essentially narrowing down the possibilities. And this restriction leads to those patterns emerging at smaller sizes, hence the lower Ramsey numbers.
So it's like saying the more specific your search criteria are, the easier it is to actually find what you're looking for.
Exactly. And the paper takes it a step further, drawing a fascinating parallel to algebraic geometry. It hints that there might be a deeper connection between Ramsey theory and the study of algebraic varieties, suggesting a whole new world of possibilities for research.
That connection to algebraic geometry is super intriguing. Can you elaborate on that a bit?
Remember our analogy of indicator polynomials as detectors for specific colorings? Well, in algebraic geometry, there's a similar idea, the vanishing set of a polynomial. This set is all the points where a particular polynomial equals 0.
So it's like the solution set for that polynomial equation.
You got it. And a lot of times, these vanishing sets have a beautiful geometric structure. They can form curves, surfaces, or higher dimensional objects called algebraic varieties.
So is the paper suggesting that the set of colorings containing a specific pattern might also form a kind of variety within the larger space of all possible colorings?
That's the exciting idea the paper is putting forward. Christopherson doesn't fully explore this connection, but the analogy is definitely compelling. It hints that we might be able to use tools and techniques from algebraic geometry to study these special sets of colorings and, by extension, gain a deeper understanding of Ramsey numbers.
That opens up a whole new avenue for research, connecting these two seemingly distant areas of math. But let's not get too lost in the abstract. The paper also applies these generalized Ramsey numbers to some very concrete problems in number theory, and that's what I'm really excited to discuss.
Yes, that's where the real power of this framework shines through. In the next part of our depth dive, we'll see how Christopherson connects these generalized Ramsey numbers to famous problems like the twin prime conjecture and the Green-Tell theorem. It's a surprising and insightful application that really demonstrates the wide-reaching implications of his work.
Welcome back. We've seen how Christopherson has built this incredible framework for analyzing these generalized Ramsey numbers, but now I'm really curious to see how it all ties into some of those big unsolved mysteries in number theory.
This is where the paper really gets exciting. Christopherson shows us that these generalized Ramsey numbers can be used to reframe some of the most famous problems in number theory. It's like he's giving us a whole new perspective on these age-old challenges.
The key seems to be this idea of metrical colorings. The paper mentions them as a way to connect graph theory and number theory. Can you explain how that works?
Absolutely. So in your typical graph coloring, we're assigning colors to the edges of a graph, right? But with a metrical coloring, we assign colors to the distances between points in a metric space. Instead of coloring edges, we're coloring the gaps between numbers.
So we're basically taking this geometric idea of distance and translating it into the world of colorings.
Exactly. It's like we're building a bridge between these two different areas of math. The paper defines metrical coloring, written as D, and it comes from a metric space, YEE, and an injection from the vertices of a graph G to Y. The colors, in this case, are the distances between the images of the vertices under A measured using the metric D.
It's like we're taking a bunch of numbers, putting them on a number line, and then coloring the spaces between them based on how far apart they are. Can you give me a specific example?
Of course. Let's take the set of prime numbers, for instance. Imagine we build a complete graph where each vertex represents a prime number. Then we can color each edge with the difference between the two prime numbers it connects. It gives us a really cool visual representation of the gaps between prime numbers.
That's a great way to visualize it. So how does this connect to actual number theory problems? The paper mentions the Green-Tell theorem.
Right. The Green-Tell theorem is a huge result in number theory. It says that for any length you choose, you can always find an arithmetic progression of primes of that length. Basically, it means you can find a sequence of prime numbers that are equally spaced out on the number line, no matter how long you want that sequence to be.
So it's like saying that prime numbers have a hidden order, even though they seem to appear randomly.
Exactly. And what Christopherson does is show us how the Green-Tell theorem can be rephrased in terms of Ramsey numbers. He translates the idea of arithmetic progressions into the language of graph colorings and Ramsey numbers.
So we're using these metrical colorings based on prime numbers to build a specific Ramsey base.
Yes, and the paper states this connection formally in Theorem 8. It defines a Ramsey base, G, SM, where G is a sequence of complete graphs and SM is made up of metrical colorings defined using prime numbers.
Okay, so we've got our Ramsey base. How does the Green-Tell theorem fit into this picture?
Well, Theorem 8 says that finding an arithmetic progression of length to a gap of k among the primes greater than or equal to the mth prime is the same as finding a specific Ramsey number. This Ramsey number uses the base we just talked about, and a Ramsey symbol that represents a path graph of length c.
So finding these arithmetic progressions of primes is equivalent to finding specific Ramsey numbers.
That's the amazing connection. And it goes beyond the Green-Tau theorem. Christopherson shows us how the same approach can be applied to other famous problems in number theory, like the twin prime conjecture, Zhang's bounded prime gap theorem, and Polignac's conjecture.
Wow. Let's start with the twin prime conjecture. It states that there are infinitely many pairs of prime numbers that differ by 2, like 11 and 13. It seems so simple, but it's been a really tough problem to solve.
I know, right? The twin prime conjecture has been stumping mathematicians for ages. But Christopherson gives us a new way to think about it using Ramsey theory. He shows that the twin prime conjecture is equivalent to the existence of an infinite family of specific Ramsey numbers.
So if we can prove that these Ramsey numbers exist, we've proven the twin prime conjecture.
That's the incredible possibility this paper presents. It's like he's handing us a new set of tools to tackle these problems. Of course, we don't know for sure if this new perspective will lead to a solution, but the connection itself is profound.
And it goes even further than that. The paper also connects to Zhang's bounded prime gap theorem and Polignac's conjecture. What can you tell us about those connections?
Zhang's theorem, which was a big deal when it was proven in 2013, says that there are infinitely many pairs of primes that differ by less than 70 million. It's a huge step towards the twin prime conjecture, but it doesn't quite get us all the way there. Christopherson shows that Zhang's theorem can also be rephrased using Ramsey numbers.
So even though Zhang's theorem doesn't completely solve the twin prime problem, it still has a connection to Ramsey theory.
Exactly. And Polignac's conjecture takes things even further. It says that for any even number, there are infinitely many pairs of prime numbers separated by that gap. It's like a supercharged version of the twin prime conjecture. And you guessed it, Christopherson demonstrates that Polignac's conjecture can also be expressed using Ramsey numbers.
It's amazing how these different areas of math, like combinatorics and number theory, are so interconnected.
I know. It's like Ramsey theory is a secret code that unlocks hidden truths about the structure of numbers.
So as we wrap up our deep dive into Christopherson's work, what are the big takeaways? What surprised you the most?
For me, the most surprising thing is how powerful and far-reaching this generalized approach to Ramsey theory is. It's not just some abstract theory. It has the potential to crack some of the toughest problems in number theory.
It's like he's given us a brand new way to look at these problems, a whole new toolkit to explore them. The connections he's made are mind-blowing and suggest a really exciting path for future research.
Absolutely. And while we still don't know if these new connections will lead to solutions for problems like the twin prime conjecture, one thing's for sure, Christopherson's work has opened up a whole new chapter in the study of both Ramsey theory and number theory.
It really shows the power of abstract mathematical thinking and how it can reveal these hidden links between different areas of knowledge. Thanks for joining us on this deep dive. We hope you've gained a newfound appreciation for the beauty and depth of Ramsey theory and its unexpected connection to the world of numbers. Welcome back to the deep dive. Today we're tackling a paper called Ramsey Theoretic Characterizations of Classically Non-Ramseyian Problems.
Oh, wow. That sounds pretty dense.
It is, but also fascinating. You know how much I love when different areas of math kind of unexpectedly connect?
Right. Like seeing the hidden links between things.
Exactly. And this paper, well, it blew my mind a bit. They're using a generalized idea of Ramsey numbers, going way beyond just like coloring graphs and pigeons.
Okay, so expanding the scope of Ramsey theory, I'm intrigued. What kind of problems are they even looking at with this?
Well, they're diving into some heavy stuff. We're talking Green-Tau theorem, even the twin prime conjecture.
Whoa, those are some big hitters in number theory. Using Ramsey theory for those. Color me curious.
But hold on, let's not get ahead of ourselves. First, we got to lay down some groundwork. They're using this new, broader definition of Ramsey numbers, building on the classic concept, but
yeah, classic Ramsey numbers, those tell us like the smallest set you need to guarantee a specific pattern will show up. Like how many people at a party, so you're guaranteed 3, either all know each other or are total strangers.
Perfect example. It's all about finding that inevitable regularity, even in systems that seem kind of random. And this paper, they take that and run with it.
So how do they generalize it? What's the new twist?
So instead of just complete graphs and those monochromatic subgraphs, they allow for more general graphs and colorings. They use these terms Ramsey base and Ramsey symbol.
Okay, so Is the Ramsey base like the playing field then? Like a sequence of graphs getting bigger and each level has its own rules about the coloring?
You got it. Great way to picture it. Then the Ramsey symbol, that's like the target. It says what subgraphs we want to find and how their edges should be colored.
I see. So instead of just, are there 3 people all connected? It's like, is there a group of 4 arranged in this specific way with relationships defined by the different colored edges?
You nailed it. And the Ramsey number itself, that's like the level where no matter how we color things, we're guaranteed to find what the symbol describes.
It's like a threshold where order just has to emerge from the mess.
Exactly. Now, the paper gets into different categories of these generalized numbers, like exact ones, where at every level of our base, there's a subgraph matching one from our symbol.
So we know for sure one of our target patterns is always there at each step.
Yeah, a guaranteed starting point. Then there's Galois type numbers, a bit more specialized.
Ooh, Galois type. Sounds fancy. What makes them special?
We're working with finite fields then, think prime numbers. And the colorings are elements from that field. It lets us use algebra, which is where things get really cool.
Algebra, my favorite. Can't wait to see how they bring that in.
Me too.
Huh?
But first, they've got some key definitions, like definition 2, which lays out formally what a graph coloring is.
Okay, that seems pretty basic. Just assigning values, our colors, to the graph's edges.
Right, so not just lines between points anymore, lines with specific colors, adding a whole new layer of info.
And that's crucial to Ramsey theory because we're looking for patterns within those colored graphs.
Exactly. Now, definition 3, this introduces the idea of an isomorphism set.
Isomorphism set. That's about grouping subgraphs that have the same structure, right? Even if their vertices have different labels.
Like a triangle is a triangle, whether its points are called A, B, C, or 1, 2, 3.
Exactly. We care about the shape, not the specific names, when hunting for patterns.
Definition 4, then, this gives a more nuanced way to define those classic Ramsey numbers, sets the stage for the generalized one later.
It's like highlighting those core elements, the complete graph size, how many colors, and whether a monochromatic subgraph of a certain size must exist.
It's the blueprint of the logic behind Ramsey theory itself.
Right, capturing that essence of guaranteed substructures within a larger structure.
Okay, and then finally, we get to the heart of it. Definition 8. This is where they unveil those generalized Ramsey numbers, encompassing all those special cases we talked about.
This is where things get juicy. What's this definition look like?
Well, it uses arbitrary sequences of graphs for both our base and symbol, instead of sticking to just complete graphs and monochromatic subgraphs.
So, way more freedom. We can explore all sorts of patterns and structures now, not just the basic ones.
It's like taking that blueprint from definition 4 and saying, okay, now make it infinitely expandable.
Love that. Really captures the feeling of expanding the scope of Ramsey theory.
And it all builds on what we talked about.
Yeah.
The base, the symbol, the idea of graph coloring.
It's like a perfect example of math definitions building on each other, creating a language that gets more and more powerful.
Absolutely. And they define even more specialized types,
Huh.
like the exact and Galois ones we mentioned, so we can focus on families of problems that are easier to analyze.
A whole toolkit for tackling these Ramsey problems.
You got it. And one of their coolest tools is the concept of indicator polynomials, defined in definition 13.
Ah, here comes the algebra. I was wondering when it would show up.
These polynomials are like mathematical detectives searching for those colored subgraphs we're interested in.
So instead of eyeballing a graph for a specific pattern, we just plug its coloring info into this polynomial and see if it equals 0.
That's it. And lemma 2, this proves that it works. If the polynomial is 0 for a coloring, bam, that coloring must have the subgraph we're looking for.
It's like the polynomial is shouting, aha, found it.
Love that. And lemma 3 takes it further. We could use multiple polynomials to search for a whole bunch of patterns at once.
So if the product of all those polynomials is always 0, no matter the coloring, then we know at least one of our target patterns has to be there.
Powerful stuff. We get a guarantee that some order exists, even if we don't know exactly what it'll look like. And this is where those Galois-type Ramsey numbers really shine. Theorem 3 shows how these polynomials can be used to pinpoint them when the number of colors is a prime power.
Right, so Theorem 3 says the highest level in our base, where the polynomial isn't always 0, that level is 1 less than the Ramsey number itself.
So finding that tipping point where the polynomial suddenly starts being 0 everywhere, boom, we found our Ramsey number.
Like finding the exact point where order emerges from all those possible colorings? Beautiful.
And corollary 1 takes it deeper into algebra, saying if the Galois-type number exists, its polynomial has to belong to a specific type of ideal.
Ideals. So we're connecting this to algebraic geometry now. That's a whole new toolbox we can use.
Exactly. And Corollary 2 extends this to cases where we limit the allowed colorings in our base.
So even with constraints on the colors, the polynomials still help us find those Ramsey numbers.
It shows just how flexible and powerful this approach is. Now check out Theorem 4. It shows we can actually convert any Ramsey number with locally finite colors, meaning any finite set of colors, into a Galois-type Ramsey number.
Whoa! That's a bridge between the general case and the more specific Galois type, so we can always use algebra, even with a wider range of colors.
Like we've got a universal translator for math.
Love it. And then Theorem 5, this extends Corollary 1 to these broader Ramsey numbers, showing that the polynomial ideal connection holds strong even when we're not dealing with prime power colorings.
The connections run deep, right?
Yeah, really deep. Then there's Theorem 6, which brings it all together beautifully.
Theorem 6 says we can figure out a locally finite type Ramsey number just by looking at whether the allowed colorings at each level of our base are contained in the zero set of the corresponding polynomial.
So those polynomials, they're our guides again, showing us where the order pops up within all those possible colorings.
It's like they're a map leading to the hidden structure in these seemingly chaotic systems.
This is really impressive work, expanding classic Ramsey numbers, connecting it to other areas, plus introducing these powerful algebraic tools.
I'm with you. But the truly mind-blowing part is still to come. They actually use all this to tackle some of the biggest unsolved problems in number theory.
Okay, now I'm on the edge of my seat. Can't wait to see how they link Ramsey theory to those famous number theory conjectures.
That's where we'll pick up in part 2 of this deep dive. Arithmetic progressions, twin primes, the whole shebang. Stay tuned for the next installment of our mathematical adventure. Welcome back to the deep dive. Last time, things were getting really exciting. We're about to see how they connect these generalized Ramsey numbers to, well, some seriously big, unsolved problems in number theory.
Yep, the heavy hitters. I'm ready for the mind-blowing connections.
Right, so buckle up. They start by tackling the Green-Tau theorem. You know, the one about finding arbitrarily long arithmetic progressions in the prime numbers.
Right. No matter how long a sequence you want, there's always a sequence of primes with that constant difference.
And get this. They showed this theorem can actually be rephrased using Ramsey numbers. It's like Ramsey theory is the secret decoder ring for number theory.
Oh, really? How did they even make that connection? Those seem like such different concepts.
It's clever. They introduced this twist on graph coloring called metrical colorings. Now, the colors are actually distances between points in a metric space.
Wait, so instead of red, blue, green, we're using like how far apart numbers are as our colors.
Exactly. And the metric space here, it's just the non-negative integers with the usual way of measuring distance.
So like if I have 5 and 8, the color of the edge between them would be 3, since that's their difference.
Nailed it. And Theorem 8, this is the kicker, it shows that finding an arithmetic progression of length, t, with a gap of k within the primes, is the same as finding a specific Ramsey number using these metrical colorings.
So if that Ramsey number exists, we know we can find that progression in the primes. Mind blown. It's like they've given us a map to these special sequences.
Totally. It's a whole new way to see the structure of prime numbers through this Ramsey lens.
And hold on, it gets better. Corollary 3, this builds on Theorem 8 and shows that a whole family of these Ramsey numbers with the metrical colorings, they actually exist for all values of 2.
Not only can we rewrite Green-Tau using Ramsey numbers, but we also know those specific numbers exist. It's a guarantee those progressions are out there.
This is incredible. Like Ramsey theory is providing this whole new framework for understanding prime number patterns.
And guess what? They don't stop there. They go for the twin prime conjecture next.
Yeah.
You know, are there infinitely many prime pairs that differ by just 2?
Oh man, one of the biggest mysteries in number theory. What do they do with that?
Theorem 9, my friend. It says proving the twin prime conjecture is equivalent to proving a certain family of Ramsey numbers exists. Again, using those metrical colorings.
So crack the Ramsey problem and you've cracked the twin prime conjecture. Seriously.
Exactly. It's like those Ramsey numbers are the keys to unlocking some massive number theory secrets.
This connection is blowing my mind. They've linked these two seemingly unrelated parts of math.
And they don't even stop at twin primes. They hit Zhang's bounded prime gap theorem and even Paulignac's conjecture, both about finding infinitely many prime pairs with certain differences.
So basically, a whole bunch of number theory problems, all reframed using Ramsey theory.
You got it. Theorem 10, that's for Zhang's theorem, where there's a bounded gap between infinitely many prime pairs. They use a slightly tweaked version of the metrical colorings, limiting the allowed colors in a specific way.
So they're making the Ramsey problem more specific, but maybe easier to actually solve.
Right. And Theorem 11, this is the grand finale. Pollingac's conjecture, infinitely many prime pairs with any even difference, they show that can be rephrased using these generalized Ramsey numbers too.
It's like they've built a whole new language for understanding this class of number theory problems, all using Ramsey theory.
And the cool part is, they don't just rephrase things, they offer tools and insights that might actually help solve these conjectures.
Right, now that's what I'm talking about. What kind of tools are we talking?
Remember those indicator polynomials?
Mm-hmm.
And the connections to algebraic geometry? That opens up a whole new path. By turning number theory into algebra, we might be able to use super powerful tools from algebraic geometry to crack these problems wide open.
Sounds like they've given us a high-tech toolkit for solving some of math's biggest mysteries.
But before we get too lost in those possibilities, let's zoom back in on the specifics. We've talked big picture, but I think it's time to roll up our sleeves and get into the nitty-gritty of some proofs.
Sounds good to me. Let's start with Theorem 1, the one about those X resolutions.
Right, X resolutions. Simplifying a Ramsey problem by focusing on the levels where we're guaranteed to find those colored subgraphs from our symbol.
Like trimming the fat, getting to the good stuff.
So how does it work? How do they prove we can simplify without losing crucial info? Well, the proof is pretty slick. It uses this hereditary property of the Ramsey base. It means the graphs in the sequence are nested in a specific way, like Russian dolls.
Each one fitting inside the next bigger one.
You got it. Each graph contains all the smaller ones as subgraphs. And using that, they argue that if a Ramsey number exists for the original base, it has to exist for the X resolution too, and with the same value.
So we can toss out those irrelevant levels without messing up the result. Handy.
Right. Then we have lemma 1, a kind of partial converse to Theorem 1. If a Ramsey number exists and has a uniform symbol, then the base must have an X resolution.
Hold up, uniform symbol. Don't think we've hit that term yet.
Oh yeah, they defined that earlier. It just means all the colored subgraphs in the symbol have the same number of vertices.
Okay, so lemma 1 says if we've got a Ramsey number for a base with that kind of symbol, there's got to be an X resolution to simplify things.
It's like a two-way street. X resolutions give us Ramsey numbers, and Ramsey numbers tell us X resolutions exist.
Back and forth, very elegant. There's a deep connection there between how the base is structured and whether these special numbers even exist.
Now, onto those indicator polynomials from definition 13. These are the stars of the show, turning Ramsey problems into algebra we can work with.
I've been waiting for this. Remind me how they work again.
The definition 13 might look scary at first glance, all those products and exponents, but the idea is simple. It's built to be a detector for the exact colored subgraphs we want.
So we plug in the coloring info, and if it spits out 0, we know the pattern's there.
Bingo. And lemma 2, this is the proof. 0 result means that subgraph must be present in that coloring.
Gotcha. Found the pattern.
Then lemma 3, we level up again. Multiple polynomials searching for a whole bunch of patterns all at once.
So if their product is always 0, no matter how we color things, at least one of those patterns is guaranteed to exist.
It's like a mathematical promise. Order will emerge, even if we don't know what it'll look like yet. And here's where the Galois-type numbers come in again. Theorem 3 shows us how to use these polynomials to nail down these numbers specifically when we're working with a prime power number of colors.
Theorem 3, that was the one about the highest level where the polynomial isn't always 0, right? And that level's one less than the Ramsey number itself.
Precisely. Find that tipping point where the polynomial starts being 0 everywhere and boom, you've got the Ramsey number.
Like catching the exact moment order crystallizes out of the chaos.
Now, corollary 1, this one dives deeper into the algebra side. It says if that Galois-type number exists, its polynomial has to belong to a particular kind of ideal.
Ideals, it's algebraic geometry. If we're bringing in big guns now.
And corollary 2 shows this same idea works even when we restrict which colorings we allow in our base.
So even with limits on our colors, the polynomials still guide us to the Ramsey number.
It's powerful stuff. Then we come to Theorem 4. This gives us a way to convert any Ramsey number with locally finite colors, meaning any finite set of colors, into a Galois-type number.
So we can bridge the gap between the general case and the special Galois case. Algebra works even with more colors.
So we've got a universal translator for math.
And Theorem 5 extends that earlier connection to ideals to this wider class of numbers. It shows that link between polynomials and ideals holds strong even when we're not limited to just prime power colorings.
It's all connected way more deeply than we might have thought at first.
Right. And then Theorem 6, this brings everything together so elegantly.
It says we can figure out a locally finite type Ramsey number just by checking if the allowed colorings at each level are contained within the zero set of that polynomial.
Those polynomials are our guides again, showing us the path to order within all the possible colorings.
They're like a map leading to the hidden structure in all this apparent chaos.
Now, the paper doesn't stop there. They go even deeper into lemma 4 and 5, which reveals some really cool things about how manipulating the Ramsey symbol, or the allowed colorings, affects the Ramsey number itself. Want to explore those?
Absolutely. Lemma 4 and 5, let's get into it. They're all about how changing the Ramsey symbol or the allowed colorings can actually change the Ramsey number itself, right?
You got it. Lemma 4 specifically looks at what happens when you make the Ramsey symbol bigger. Remember, that's the set of those colored subgraphs we're trying to find.
Right, like we're expanding our search looking for more patterns.
Exactly. And lemma 4 shows kind of intuitively if you add more colored subgraphs to the symbol, the Ramsey number can only get smaller or stay the same. It's monotonic, they call it.
Makes sense. The more patterns you're looking for, the sooner you're guaranteed to hit at least one of them, like casting a wider net.
Great analogy. And the proof, it all comes down to those indicator polynomials again. The polynomial for the original symbol, it'll be a factor of the polynomial for the expanded symbol.
So if the original one's 0 for a coloring, meaning we find one of those original patterns, the expanded one has to be 0 too. We're guaranteed to find something from the bigger set.
It's really neat how the algebra of the polynomials mirrors what's happening with the Ramsey problem itself. Math is so interconnected.
It's beautiful. Okay, so lemma 5, this one goes the other way. What if we restrict the colorings we're allowed to use in the base?
So instead of more options, we're limiting the color combinations.
And lemma 5 says, again, kind of intuitively, if you reduce the coloring choices, the Ramsey number can only go down or stay the same.
So less freedom with colors actually makes it easier to find those patterns. It's like getting rid of distractions so the order is clearer.
It's exactly. The proof for this one's pretty straightforward. If a coloring follows the stricter rules, it automatically follows the original looser rules.
So if the polynomial's 0 for the restricted set of colorings, meaning we've got a pattern, it's got to be 0 for the original set too. Same guarantee.
Simple but powerful. These two lemmas together, they really show how the combinatorial stuff and the algebra and Ramsey theory work together.
Yeah, they're tools to play with and analyze these problems, and they set us up to understand the structure of these numbers even better.
Speaking of understanding better, the paper also connects this all to Galois connections. You know, those special pairs of functions that link elements in partially ordered sets.
Things are getting fancy now. So they're saying we can view Ramsey numbers through this Galois connection lens, where the ordering is all about whether subgraphs are included and how the colorings are restricted.
So it's not just about the number itself, it's about the relationships between everything.
Oh, wow.
The graphs, the colorings, the patterns we're hunting for.
A whole new way to explore the structure of Ramsey theory itself.
Like a new map for this crazy mathematical landscape.
And this is just the beginning, right? This paper's opened up so much, a deeper understanding of Ramsey theory, how it links to other areas, its potential for solving those massive number theory problems.
This deep dive has been a wild ride. From simple graph coloring to the frontiers of number theory, who knew it would go this deep?
It's amazing how that pigeonhole principle, something so basic, leads to these huge, unexpected connections across math.
And the power of algebra. Those indicator polynomials, ideals. Who would thought they'd be useful for something like the twin prime conjecture?
It just shows math isn't a bunch of separate things. It's all woven together.
Yeah.
Exploring those connections, it's how we see the real beauty and power of it all.
So wrapping up, I think it's safe to say this paper is a game changer. Expands Ramsey theory, links it to number theory, gives us awesome tools for future work.
Couldn't have said it better myself. Anyone who loves math needs to check this out. And it leaves us with so many questions, so much more to explore.
Huge thanks for joining us on this deep dive into the world of Ramsey theory. Hope you enjoyed the ride. Until next time, keep that curiosity burning and keep diving deep into all the amazing things math has to offer. All right, folks, ready to dive deep. Today, we're taking on Ramsey theory, specifically this paper that's proposing a whole new way of looking at Ramsey numbers.
It sounds like a challenge.
It definitely is. We're talking about a super generalized approach. Plus, they're linking it to some of those big unsolved problems in math. You know, the ones that keep mathematicians up at night.
Oh yeah, those are always fun.
Well, let's see if this paper sheds any light on them. First things first, they give us this brand new definition of Ramsey numbers. It's not just about those classic complete graphs and monochromatic subgraphs anymore.
It's definitely broader than that.
Yeah.
They're considering any kind of subgraph with a specific coloring.
Exactly. It's like they've blown open the doors of what we can analyze with Ramsey theory. So how are they capturing this broader scope with their new definition? What's the core idea?
Well, they use this notation, Robbie BSF.
BSF. Okay, break that down for me.
Sure. $1 is like the foundation. They call it the Ramsey base. It defines what types of graphs we're working with and how they can be colored.
So Bido sets the stage. Got it. What about $7?
$7 is our target. It's called the Ramsey symbol. It specifies the subgraph we're searching for and its exact coloring pattern.
So $5 is the playground and $7 is the hidden treasure we're trying to find. What's $1 then?
$5 is the rule book. It's the set of all the allowed coloring functions, like what colors we can use and how we're allowed to color the edges.
Okay, so Bido defines the world, dollars are the goal, and Fido tells us how we can play the game. It's pretty flexible. Now, they talk about two ways to think about these generalized Ramsey numbers, one through colorings and the other through embeddings. How do those two connect?
Okay, so the coloring perspective, that's all about, looking at a specific coloring and seeing if you can find that target subgraph with that exact coloring.
So, like trying to strategically color a graph to avoid creating the specific subgraph we're looking for, kind of like a game of hide and seek.
Yeah, exactly. Like you're trying to hide that subgraph within the larger graph. Now, the embedding perspective, that's kind of the flip side. It's about taking that subgraph and seeing if you can fit it into the larger graph, making sure the colors line up, respecting those coloring rules from $5.
Like a puzzle then.
Yeah.
We've got these colored pieces,
Yeah.
and we need to see if they can fit together in a way that matches the overall pattern.
Yeah, you got it. And what's cool is the paper shows that these two perspectives are actually the same thing. Whether you try to color to avoid the subgraph or try to fit the subgraph in, it boils down to the same conditions.
A nice duality there. Gives us two different ways to attack the same problem. Now, they throw in a bunch of specific types of Ramsey numbers. Monochromatic, rainbow, lexicographic, size Ramsey numbers. What's going on there? Are they just showing off how their fancy new definition can handle all these special cases?
I think that's part of it, yeah. They're demonstrating how their framework is general enough to encompass all these different flavors of Ramsey numbers.
Give me an example. How do they handle those classic monochromatic Ramsey numbers, the ones we usually encounter?
Well, remember, those are the ones where we're looking for a subgraph that's all one color within a complete graph. So in their framework, you'd set the Ramsey base, $, to be the set of all complete graphs.
Okay, so that sets the stage for the classic scenario. Then what?
Then the Ramsey symbol, $7, that becomes just a single graph representing the complete subgraph we're looking for, and it's colored with a single color.
Right, the target is just a one-colored subgraph.
Right.
And $5, I bet, only allows for that one color.
Exactly. $5 restricts the coloring functions to just that single color.
So they're basically setting up the parameters to match the classic monochromatic setup. Pretty neat. And they do something similar for the rainbow, lexicographic, and size Ramsey numbers, right?
Right. They show how each of those special cases can be represented by defining a $, and $5 in specific ways.
It's like they've built a master key that can unlock all these different doors in Ramsey theory. Now, they spend some time talking about these exact Ramsey numbers. What makes those so special?
Exact. Ramsey numbers are all about situations where the subgraph has to appear with a specific coloring. No variations allowed.
So it's not enough to just find a subgraph. It has to be colored in a very precise way.
Exactly. And they're important because they kind of form a foundation. They help us understand more complex cases.
So master the basics before trying the fancy moves, right?
That's the idea. And the paper shows a cool trick for turning non-exact Ramsey numbers into exact ones.
Oh, how do they do that?
They basically tweak the Ramsey base and symbol in a way that forces the subgraph to appear with that specific coloring. It's like they're transforming the problem into a simpler, more manageable one.
Clever. It's like they're finding a way to reduce the complexity without losing the core of the problem. Okay, but now let's talk about the part that really grabbed my attention. Polynomials. They bring up these indicator polynomials to represent coloring patterns on graphs. Now, my polynomial skills could use some dusting off. Can you break down how these polynomials work and why they're so useful here?
All right, so picture a graph with edges colored, let's say red and blue.
Okay, got a colorful graph in my mind.
Now, for each edge in the graph, we assign a variable in the polynomial, and we construct the terms of this polynomial in a very specific way. The idea is that if you plug in values for those variables that represent the coloring of the graph, like maybe 1 for red and 0 for blue, the polynomial will only equal 0 if a particular colored subgraph exists within that graph.
So the polynomial basically encapsulates the whole coloring pattern of the graph in one neat expression.
Exactly. And not just that, it can also help us determine whether certain subgraphs with specific colorings exist within the larger graph.
So like a detective, but for graphs.
Yeah, kind of. Like, let's say you're looking for a red triangle within your red and blue colored graph.
Okay, searching for that red triangle.
You can build a specific indicator polynomial that will only equal 0 if and only if that red triangle exists in your graph.
Wow. So you plug in the colors of your graph into this polynomial, and it acts like a detector, telling you whether your target is hiding in there.
Exactly. And what's really powerful about this is that now we can use all the tools of algebra to analyze these graph coloring problems. We can manipulate these polynomials, study their properties, and uncover relationships that might not be obvious just by looking at the graphs themselves.
It's like they've built a bridge between the world of graphs and the world of algebra using these polynomials. Opens up a whole new toolbox for tackling Ramsey problems.
So the twin prime conjecture, right? It's about whether there are infinitely many pairs of prime numbers that are only 2 apart. Sounds simple enough.
Yeah, deceptively simple. But proving it, that's a whole other story. Mathematicians have been wrestling with that one for ages. So how do they even begin to connect this to Ramsey theory? It seems like a completely different beast.
Well, they use a similar approach to what they did with the Green-Tau theorem, but they get really clever with how they build the Ramsey base and symbol. Like before, they start with complete graphs, and each point, each vertex, represents a prime number.
Okay, keeping that visual in mind. But you said there's a twist.
There is. They add a restriction to the coloring.
Ooh, a restriction. Tell me more.
So in each graph, they require a path that represents the sequence of prime numbers, starting from the smallest prime in that graph.
Okay, so it's not just about the difference between primes anymore. It's also about their order.
Exactly. You have to include that path of consecutive primes as part of the coloring scheme.
So if we've got a graph with primes 2, 3, 5, and 7, the path 2, 3, 5, 7 has to be there. No more random coloring just based on differences.
Right. It forces us to consider the way primes are arranged. And now, get this. The Ramsey symbol they choose is super simple. Just a single edge colored with the number 2.
Wait, hold on. Just one edge, colored 2. How does that tie into finding twin primes?
Remember, the way we're coloring these graphs is based on the differences between the primes. So if you find an edge colored 2, that means the 2 primes connected by that edge are exactly 2 apart.
Uh-huh. Finding that specific edge in this very specific coloring is the same as finding a twin prime pair.
You got it. And that's the beauty of it. It's so elegant. This simple setup captures the whole essence of the twin prime conjecture. If this particular Ramsey number with this base and this symbol exists for all sizes of complete graphs, it would mean we can always find twin primes no matter how far we go in the sequence.
It's incredible. They've transformed this super challenging number theory problem into a question about the existence of a specific Ramsey number. Really showcases the potential of their framework.
Absolutely. And they don't stop there. They go on to tackle Polignac conjecture, which is like a souped-up version of the twin prime conjecture.
Right. Polignac's conjecture says that for any even number, there are infinitely many prime pairs with that specific difference. So twin primes are just a special case where the difference is 2. How do they handle this more general case?
Same overall strategy, but they adapt the coloring to handle that arbitrary even gap. Still using complete graphs, vertices as primes, and keeping that path of consecutive primes.
Sounds familiar so far. What's the key change?
Instead of coloring all the edges based on the gap, they focus on coloring the edges that are not part of that required consecutive prime path. And they color them based on whether the difference between the primes they connect is equal to the gap we're looking for.
Okay, so the edges on that prime path keep the order, and the other edges tell us if we've found a pair with the right difference.
Exactly. And you guessed it, the Ramsey symbol becomes a single edge colored with the specific even gap we want.
So if we're looking for prime pairs with a gap of 6, the Ramsey symbol would be an edge colored 6. And finding that edge within this specific coloring would mean we found a prime pair with that difference.
Precisely. The paper shows that if this Ramsey number with the right base and symbol for our chosen even gap exists for all complete graphs, then Polignac's conjecture holds true.
It's like they've cracked the code. They've used this Ramsey framework to reframe not one but two of the biggest unsolved mysteries in number theory. Really makes you wonder what other hidden connections are out there waiting to be discovered.
I know, right? It's like they've opened a whole new door into the world of number theory. It's a testament to the power of abstract thinking, finding these unifying principles across different areas of math.
And don't forget those indicator polynomials. They're kind of the engine behind all of this.
Oh, absolutely. They're crucial. Remember, they give us a way to represent and analyze graph colorings algebraically. Each edge gets a variable, and the polynomial is built so that it only equals 0 if a specific colored subgraph exists.
Yeah, they act like these pattern detectors, telling us if a specific arrangement of colors is hiding in the graph.
Right. But they can do even more than that. We can also use them to count how many of those subgraphs are in a graph.
Wait, so we can not only detect the pattern, but also count how many times it appears.
Yep, that's right. And that ability to count is really important for proving some of the key results in this paper. Like when they connect Ramsey numbers to the Green-Tau theorem, they use these polynomials to count how many arithmetic progressions of a certain length you can find within the prime numbers.
So they're turning the problem of finding patterns in prime numbers into an algebra problem, counting the solutions to these polynomial equations.
Exactly. It's a brilliant translation from combinatorics to algebra, and it allows them to use all the powerful tools of algebra to analyze these number theoretic concepts.
It's amazing how they bridge these different areas of math. They don't stop there, though.
Yeah.
They also show how these indicator polynomials can help us understand the structure of Ramsey numbers themselves.
Oh yeah, they get really deep into that. They show how the algebraic properties of these polynomials can give us clues about how Ramsey numbers behave as we change the underlying graphs and coloring schemes.
So it's like using polynomials to analyze the very concept of Ramsey numbers. Pretty meta.
It is, and it's incredibly insightful. For example, they prove that if you make the Ramsey symbol bigger, meaning you're looking for a larger or more complex colored subgraph, the Ramsey number generally gets bigger too, assuming it even exists.
That makes sense. If you're looking for a more complicated pattern, you'll likely need a bigger structure to guarantee finding it.
Right. And on the flip side, they show that if you restrict the coloring options, make the rules stricter, the Ramsey number usually gets smaller.
So fewer colors, smaller structure needed. It's interesting how these polynomials give us a way to quantify these relationships between the Ramsey base, the symbol, and the Ramsey number itself.
Absolutely. And the paper goes even further, exploring connections to algebraic geometry and Galois theory. But maybe we should take a pause here and recap what we've covered so far. It's been a lot.
Yeah, recap would be great. We've gone through a lot of dense material, and I think it's good to summarize before we keep going.
Okay, so we started with their new generalized definition of Ramsey numbers. That expands classic Ramsey theory by including all sorts of coloring patterns. Then we looked at two ways to think about these generalized Ramsey numbers, colorings and embeddings, and saw how they're actually two sides of the same coin. We talked about how their framework captures all those special types of Ramsey numbers, like monochromatic and rainbow, and we highlighted those exact Ramsey numbers as building blocks for more complex cases.
Right. Then we got into the fascinating world of indicator polynomials, which are like these algebraic tools for representing and analyzing graph colorings. We saw how they can act as detectors for specific patterns and even count how many times those patterns show up.
Yep. And then the really exciting part, how they connect those polynomials and Ramsey numbers to those unsolved problems in number theory. The Green-Tau theorem, the twin prime conjecture, Polygnac's conjecture.
Yeah, it's mind-blowing to see how seemingly unrelated areas of math can have these deep connections. Opens up a whole new way of thinking about those problems.
Totally. And as we get further into this paper, we'll uncover even more connections and applications.
I can't wait. But for now, I think we need to let all this information sink in a bit. Okay, let's get back to those polynomials. We were talking about how they can help us understand the structure of Ramsey numbers themselves. That's pretty mind-blowing.
It is. It's like going meta with Ramsey theory. They connect these ideas to algebraic geometry, specifically using those indicator polynomials to define things called algebraic sets.
Algebraic sets. Sounds complicated.
They're actually not that bad. Just think of them as geometric shapes, like curves or surfaces, that are defined by the solutions to polynomial equations.
Oh, okay. So instead of just thinking about those polynomials as abstract expressions, we can actually visualize them as defining some sort of shape or space.
Exactly. And by studying those geometric spaces, we can learn something about how the Ramsey numbers behave. It's a way to connect this world of counting and patterns with the tools of geometry and algebra.
That's a powerful link. You mentioned Galois theory earlier. How does that fit into this whole picture?
Well, remember, we're working with these finite fields. They're kind of like number systems, but with a finite number of elements. And Galois theory gives us this whole toolbox for studying those fields and their extensions. And it lets us analyze the solutions to our polynomial equations within the context of these finite fields.
So we're taking these graph coloring problems, turning them into polynomial equations, and then using Galois theory to study those equations within these special finite fields.
Exactly. It's a crazy journey, but it highlights how all these different areas of math are interconnected.
It's really amazing. They also bring up this concept of ideals.
Ah, ideals. Love those.
Can you remind me what makes an ideal so special?
Okay, so think of a ring, right? It's a set with addition and multiplication. An ideal is a subset of that ring that sort of absorbs multiplication from the outside. If you multiply something from the ideal by anything from the ring, the result stays inside the ideal.
So anything that gets too close to an ideal gets sucked in, like a mathematical black hole.
Yeah, that's a great way to think about it. Now, here's the cool part. The indicator polynomials for a Ramsey problem actually generate an ideal within a specific polynomial ring.
So we combine those conomials in different ways, and that creates this special subset, this ideal, within the polynomial ring.
Exactly. And then by studying the properties of that ideal, we can actually learn about the Ramsey number we're interested in.
It's like we're going from coloring graphs to constructing polynomials to analyzing ideals. And all of this gives us a deeper understanding of Ramsey numbers.
That's the beauty of it. They show that the properties of that ideal can tell us whether the Ramsey number even exists and, if it does, give us some clues about its value.
So we're using this abstract world of ideals to answer concrete questions about these Ramsey numbers. Amazing how they connect these ideas.
It's one of the most fascinating aspects of math, how these seemingly different areas can come together to provide a richer understanding of a concept.
And it sounds like this paper is just scratching the surface. You mentioned resolutions, hereditary sets, structural results. It seems like a treasure trove of mathematical insights.
It really is. This new approach to Ramsey numbers opens up so many possibilities. It's exciting to think about where this research might lead.
Well, this has been quite a journey. I feel like my brain is overflowing with new ideas and connections.
Mine too. It's always fun to dive into these cutting-edge topics.
To all our listeners, thanks for joining us on this mathematical adventure. We hope you're leaving with a sense of wonder at the incredible power of math and its ability to connect seemingly unrelated ideas. Keep exploring, and who knows what amazing discoveries you might make.